We have one problem here that we didn't quite finish, so we'll finish this off, and then we have one more slide, and then we'll just start reviewing. It's that time of the semester. So the very last topic is this area between polar curves. In this case, it's just between the curve and the origin. And we got down to this point. So recall that this is our area formula, 1/2 r squared. We're going to integrate that function. R is the polar function. So whatever the polar function is, we've got to square it. And then in this particular case, we're going from pi over 2 to 3 pi over 2. So that's going to give us this green half of this cardioid. And then we doubled it with symmetry to get the area of the entire cardioid. So we just have a little computation to finish off down here. We had a sine squared, which we recall has to be power reduced before we integrate. So let's just go ahead and simplify this a little bit. The division by 2 over there, let's do that, and then we can do our integration. So dividing this by 2, we get 1/2, and then 1/2 plus 1 is 3/2. So the integrand will end up being this. And then we'll have minus cosine of 2 theta divided by 2. So now we can integrate. So we'll integrate term by term. And that will give us 3 over 2 multiplied by theta minus 2 cosine of theta. The integral of sine is minus cosine. And then over here, let's think about integrating that. We have to remember our reverse chain rule. The angle is not just theta, it's 2 theta, so we'll have to do a division by 2 to do the reverse chain rule. So we're going to integrate the outside function, integrate cosine, and get sine. So we'll have sine of the same angle. And then we have to divide by 2 for a reverse chain rule, which is going to give us a 4 down in the denominator. And then we have our limits of integration, pi divided by 2 up to 3 pi divided by 2. All right, anything there cause you question? So 1/2 r squared is our main formula, and plug and chug. So let's notice that when we do our substitution here with our limits of integration, notice this term here at the end. If we plug in pi over 2, we get sine of pi, which is 0. If we plug in 3 pi over 2, we get sine of 3 pi, which is also 0. So this term is not going to contribute any area. That term is going to be 0. Let's focus on the middle term for a second. Cosine of pi over 2. So pi over 2 is up here. Cosine is the x value. That's 0. Similarly for 3 pi over 2. So this term's not going to contribute any area. So we're down to just this first term. I'll combine these constants, so that will be 24 times theta. And then we'll plug in 3 pi over 2 for theta. And then we'll subtract off the lower limit of integration. So we'll get that. 3 pi over 2 minus 1 pi over 2 is 2 pi over 2, which is pi. And we have a total of 24 pi. That will be the area of our cardioid. Last slide. So here we have a rose, so a 4-petaled rose. The equation is given to us up here. You don't need to know how to graph the roses. Those will be given to you if there is a rose in the test. Notice that when the coefficient of the angle is even, you have double the number of petals. If the coefficient of the angle was odd, you would have that exact number of petals. So once again, we want to think about plugging in thetas. We want the area of all these leaves And the best rule of thumb is to use as much symmetry as possible. It's usually the safest thing to do. Sometimes with these polar curves, you can just integrate 0 to 2 pi and it works out fine. Other times it just doesn't. And it's hard to figure out when it's going to work and when it doesn't. So to be safe, we just go with as much symmetry as possible. So I'm thinking that if we take, that color's not standing out. If we take half of a petal and then multiply it by what value?
2.
8. So if we multiply by 2, we'd get 1 petal, and if we want all the leaves, we'd multiply it by 8. So 8 would give us the total area. So if we can figure out the theta values that generate that half petal, then we're good to go. And if we think about it, think about the way we've been doing this. If we plug in a theta value, let's see what we get for r. If we plug in theta equals 0, so theta equals 0 is this direction. And if we plug in 0, we get 0. So that means we're right at the origin. Theta equals 0 gives us this point. And it appears that the tip of the petal is at pi over 4. So let's just check. So if we plug in pi over 4 up here, so if we plug in a pi over 4 for theta, we cancel a 2. We get sine of pi over 2, which is 1. 1 times 3 is 3. So sure enough, at pi over 4, we're 3 units from the origin. There's 1, there's 2, there's 3. So if we could also go to Desmos to confirm it, but if we just graph that function from 0 to pi over 4, we're going to get half a petal. So if we find that area and then multiply it by 8, we're good to go. So the area in this case, we are going to multiply by 8. And then we have this 1/2, which we can pull out to the front. We're going to go from 0 to pi over 4. And then we have r squared, that function squared. So that's going to be 9 sine squared of 2 theta d theta. So there's our setup. So the 8 is from symmetry, and then we have 1/2, and then r squared. So this will give us coefficient of 4 times 9, 36. And then inside here, we have that square on the sine, and we know that a sine squared or a cosine squared, we have to power reduce it. That's going to be 1/2 times something. I'll pull the 1/2 out in front and put it right there. So that's from the power reduction. So it's 1/2, and then it's either 1 minus or 1 plus cosine of 2 theta. Well, 2 theta in this case will make it 4 theta, and with sine, it's negative. So that'll be our power reduction. So the full power reduction has this 2 there, so 1 minus cosine 2 theta over 2. And because the theta, the angle up here is already 2 theta, when we double it, we get 4 theta. So the inside is always double when we do that. Now we can integrate. Once again, we need to use our RCR, reverse chain rule. And integral of cosine is sine of the same angle. And then we take the derivative of the angle and divide by it. And in this case, when we take a look at our limits of integration, plugging in 0 is not going to contribute any area. If we plug in 0, we get 0 here and 0 here. So we only really need to worry about that pi over 4. We'll have 18 multiplied by, let's see. If we plug in pi over 4 up here, we end up with sine of pi, and sine of pi is 0. Sine of pi is 0. So this actually doesn't contribute any area at all for either of those limits of integration. So we really just have to plug in the pi over 4 right there. Pi over 4 minus 0 is pi over 4. So pi over 4. So that is going to give us 9 pi divided by 2 as the area of everything, all 4 petals. Any question on any of those steps? last one, then we'll start our review stuff. So find the area inside the curve r equals root of cosine, and outside the circle of radius root 2 over 2. So we've seen that with polar curves, circles centered at the origin are really easy to graph. Right? That's r equals root 2 over 2. That means theta can be anything, and the r value is always root 2 over 2, so that's the circle, which means this blob-looking thing is that cosine function there, r equals the square root of cosine. And it says that we want to be inside the blob and outside the circle, so we would like this entire crescent. So we want the area of this whole crescent out here. But once again, with polar, we're going to use as much symmetry as we possibly can. So if we find the area of that yellow region, we can then double it. So the area will be 2 multiplied, so that's the symmetry 2. And then the 1/2 from the formula will just be factored to the front. And then we have to figure out r in a moment. Let's figure out our angles first. So it appears that we're going to go from 0 to pi over 3. Let's just check. If we plug in 0 in the circle, certainly we are right there. And let's just make sure we're on the same radial line if we plug in 0 to the blob. Plug in 0 here. Cosine of 0 is 1. R value is 1, so we are, in fact, right there. When theta is 0, that is the difference between the two curves. And let's check that they both are going to generate the same r value at this point here. So plugging in pi over 3, if we plug in pi over 3 for the circle, there's no theta, so the r value is root 2 over 2, which is right there. Come over here, plug in pi divided by 3. Cosine of pi over 3 is 1/2. And then we take the square root of 1/2, and we get root 2 over 2. So both curves have the same r value of pi over 3. So this tells us that we sort of can imagine this windshield wiper thing where, as we rotate this way, that's going to sort of create that half crescent. Okay, now we have a washer type scenario. The idea would be that we're going to find the area from the blob inside the blob to the origin, and then the area inside the circle to the origin. So we have to do this difference squared of the radial values. So like an r outer squared minus an r inner squared type of thing. So the outer one is the blob. So it's going to be the blob squared. So that's the outer radius squared minus the inner radius squared. And we're going to go from 0 up to pi over 3. So it's kind of like when we did the washers, we did the area, the outer area that created, if we're finding the area of a washer, we did the outer disk area minus the inner disk area. It's that same idea. And this will give us 1 out in the front, and then 0 to pi thirds, squaring that square root. And then when we square this, we get 1/2. When we integrate, integral of cosine is sine, minus 1/2 theta, 0 to pi over 3. So sine of pi over 3, that's the vertical at pi over 3, which is going to be root 3 over 2, minus pi over 6. Plugging in the pi over 3 here gives pi over 6. And then if we plug in 0, we get nothing. So this is our final answer. We could get a common denominator if we so chose. Does not matter. Either is going to be correct. That'll be the area of that entire crescent.
For that picture, will we have to be able to graph that or no?
No.
Cool.
Yeah, you would have to be able to graph that circle centered at the origin, but not anything. So the only graphs you should be able to do are the circles centered at the origin, the circles that are tangent to the origin, and then the cardioids. So that's it. All right. Any questions? Let's take a look at any questions that you might have from the Chapter 12 stuff. Does anyone have one off the top of their head or from their homework or the quizzes that you want to look at?
Is this style going to be the hardest, finding the area between two curves we'll see?
For Chapter 12, yes.
Okay.
Yeah, for Chapter 12. So if we take a look at, let's just take a look at the review sheet for a moment. So if you look at the review sheet, there is the review layout. So we're going to have 4 questions from each unit, and then all the standard stuff. Here are the topics for Chapter 12. And then if we look at a sample exam outline, kind of a little bit more precision here. So these are the most important 4 concepts. Taking a parametric curve and converting it to Cartesian. So you eliminate the t and you end up with an xy equation. And then you graph the xy equation and use any restriction that came from the parametric setup. Converting polar equations to Cartesian, finding slopes of tangents, and then finding the area between 2 polar curves. So that'll be the hardest one, is that for most people it's that polar area between 2 curves. So any polar thing, parametric thing that you have you want to look at? I heard such silence in here before. Okay, so then let's take a look at this thing, and we have a couple of ways that we can do review. We can just sort of systematically go through 1 through 12, and then 13 through 16 if we have time. We just finished sort of 16. It's totally up to you. Should we start at the beginning and do a washer or a shell?
Yeah.
Does anyone have a preference for washer or shell?
Shell.
Okay. There's no ambiguity there. Okay, so let's create a scenario. Unless you have a specific one you want to do, I'll just make one up. So let's rotate around a line that's not one of the coordinate axes, just to sort of make it as general as possible. And what seems to be the most general type of thing is when that line that we're going to rotate is in either the negative y direction or the negative x direction. So let's suppose, let's just create a nice simple geometric shape like a triangle. Let's go ahead and, well, actually, let's do a parabola. So let's do y equals x squared from 0 to 1. And we're going to take that region right there, and we're going to take all that area, and we're going to rotate it around that axis. And we'll say that that axis, let's move that axis. I don't want a fraction. Fraction's no good. I will not give you a fraction. So let's say that that's at y equals -1. Okay, so we're going to go around y equals -1. We're going to take that little, below the parabola area.
And then x equals 1?
Yes, x equals 1. X equals 0 to x equals 1. And that area right in there. So that area gets rotated. Okay, so the idea with a cylindrical shell or with any of our geometric cross sections, the first thing we need to do is find the area of that geometric cross section. And so it could be a washer, it could be a disc, or it could be a shell. And when we say cross section, we're using the word lightly. We're imagining our solid object, and when we think of cross sections for shells, we're thinking of it actually being cored, like an apple core. So when we think about building our shell, we know that that's going to be 2 pi RH. That's our generic formula. 2 pi r is the circumference of a circle, and then we multiply by h, which is the height. So that extrusion is going to give us the area of the cylinder or the area of a shell. The shell is created by rotating a horizontal element. So we've got that horizontal element, and when that green element rotates around a horizontal axis, it creates a cylinder. If we chose a vertical element, we would end up with a washer. So parallel is going to create a cylinder. Perpendicular would create a washer. So parallel, creating a cylinder. And let's identify these generic pieces. The generic pieces are the R and the H. Well, the H is the length of that horizontal element there. So whatever that horizontal distance is, that's the height of the cylinder, the height of the shell. And if we look at the distance that that element is from the axis of rotation, that's going to be called R. That's the radius. So first question is, should we be integrating with respect to x, or should we be integrating with respect to y?
Why?
Y, exactly. So we have a horizontal element, and the thickness of a horizontal element is dy. So that tells us integration with respect to y. If we had a vertical integration element, its thickness is dx, and we would integrate with respect to x. So we know that we are integrating with respect to y. So we're sort of thinking about the thickness right here. This element is at a random y. So we can think of that as just at a random y. Okay, let's figure out the height first, since we're sort of focused on that green right there. It's a horizontal distance. So when you're starting from scratch, you look at your element and you identify it's horizontal. I want to find a horizontal distance, which is the right x coordinate minus the right, it's the right x minus the left x. And if it was a vertical element, it would be the top y minus the lower y to get distance. So when we're looking at this, we have to identify, okay, well, what's the x value right there at the right endpoint? And that x value is 1. And then we come over here. We've got this curve, and we want the x value for that curve. Well, the curve is right here, and the curve is presented as a y value. When we say y equals x squared, we're sort of saying this is how we're going to focus. We're going to focus on the y value of the set of points. Well, obviously, if we want the x value, we need to do some math. What's the x value going to be? Square root of y. So the x coordinate right there is going to be square root of y. So the right x is x equals 1. The left x is square root of y. Square root of y. So that is the radius right there. Or the r, but it's just called the, not the r, the height right there. That is the height right there. The height. So we're doing height. That's height. That's height. Everyone following that? Horizontal distance, right x minus left x. The right x, the curve here is x equals 1. So all the x's are equal to 1. So the right x is 1. The left x is along a function. So we just have to isolate that letter. Isolate the x and get square root of y. Now the radial value, the r, is a vertical distance. So it's top y minus lower y. What's the top y? It's just y. It's generic. That thing can be sliding anywhere between 0 and 1. So the top y is just y. The lower y is, so it's y minus minus 1. That'll be upper y minus lower y. Or if you're more geometrically inclined, you can think of this distance right here is, this y is above the x-axis, so it's positive. So it's that distance plus whatever this distance is right here, which is 1. So you could end up with y plus 1 looking at it geometrically also. So when all is said and done here, that is our area of the shell at height y. And if we FOIL this out, we'll have 2 pi. And then in here, we're going to get a y. And then we're going to get a minus y to the 3/2. And we're going to distribute, let's see, I did that and that. Now we have to do that and that. So then minus square root of y, which is y to the 1/2. And then that's plus 1. So those are the 4 combinations that we have. So the volume is the integral of the cross-sectional area. So we integrate the area of this cylinder, and we've got it. And you told me that we were integrating with respect to y. That'll make sense because we have y's right there. So we're going to have 2 pi can come to the front, and then we have y minus y to the 3/2 minus y to the 1/2 plus 1 dy. And limits of integration, you said they're y limits, so they go from y equals 0 to whatever this y value is, which is 1. So 0 to 1. And then integrate term by term, plug in your 0, plug in your 1. Any questions on the setup? Grinding over there. Yeah, let's close that door. That noise is sounding weird. Too weird to think about now. So any step there you want to ask a question about? Anything cause you concern? All right, so you can integrate that term by term and plug in your limits. Question 2 says find arc length or surface area. What do you want to do, arc length or surface area?
Surface area.
Surface area, okay. So when we think about surface area, let's imagine, let's go with a square root function. And I'm just making stuff up, so there's a chance that we might get something that's not integrable. It's possible. Because we know that a lot of functions aren't integrable for us. But that doesn't matter. We can still set it up. So let's suppose we have y equals the square root of x from 0 to 4. And let's suppose we want to rotate it. Let's go around the, doesn't matter to me. You want to go around the x-axis or the y-axis? Does one seem more problematic? No choice? No care? Do you care?
We just did around a y-axis.
So should we go around x?
So let's do x, yeah.
Okay. So, oh, we just went around a horizontal, so we should go around a vertical. Yeah, gotcha. All right, so let's go around the y-axis. So this is going to be our axis of rotation. So we're rotating around there. And this shape is rotating around. It's going to create that funnel-looking thing, and we want the surface area of that funnel-looking thing. So when we are imagining this happening, when we're rotating, we're only rotating the curve, so we're imagining rotating this single point around, and when that single point rotates around, it creates a circumference. It creates the sort of perimeter of a circle. And that's how we think about our area formula. So our surface area formula, if we use an S to represent it, surface area, the generic formula is 2 pi r, that's a circumference. And the idea is that we want to add up all of the circumferences along the curve. So these points are along the curve, and when we think about the variable along the curve, that's s. When we're moving along a curve, that's the s variable. So we're going to add up all these circumferences along the curve, which is why we choose a ds. So that is our generic formula for the surface area. We integrate circumference along the curve. We don't know s limits, right? We don't know anything about S. We don't have a little tape measure on the curve, so we can't use S limits. We have to convert to X or Y. And so when we convert to X or Y, the 2 pi can come out to the front. And if we look at R right there, that R is a horizontal distance. What is that R value?
An X value, yeah, X.
So if we look at the curve, we want to isolate the X value. It's a horizontal distance. So horizontal means right X minus left X. The curve right now is presented as a Y value. So we want to convert that. We're going to convert it over and say X is equal to Y squared. So that's the right X. The left X is just 0. So the radius is going to be Y squared. So that's the radius. So these two, everyone okay with that? So R is the distance from the y-axis horizontally, so we just solve the curve for X. That's what X is going to measure. Now ds is converted to dx or dy. Should we convert it to dx or should we convert it to dy? dy, because we have a horizontal element, so we're going to integrate with respect to y. So this needs to be converted over, so it's going to be 1 plus, let me write it off on the side, so ds is going to be the square. We have two choices. It's either 1 plus x prime squared times dy, or if we had the other scenario, ds would be 1 plus y prime squared dx. So it just depends if you're going around the x-axis or the y-axis. So we're in this scenario right here, 1 plus x prime squared. So we have x right here. What is x prime?
2y, y prime.
2y. So x prime will be, so this is dx dy. So the dy is built in. If you convert just the, so if we wrote it in differential notation, you're thinking of it like that. Dx would be 2y dy. But they're asking us for x prime, so we're in this scenario. So dx dy is 2y. So when we square it, we get 2y quantity squared. So we don't need to break it down into differentials. So, but that's what you would do on what you said, Sam.
Okay.
If we needed to, but we don't need to here. So x prime is 2y. So that's dx dy. And then we have a dy on the outside. So that's our ds. What does this represent if we weren't integrating 2 pi times y squared? If we were just integrating the green, what would we be getting?
Arc length.
Arc length. That would just be arc length. The 2 pi r is circumference. So 2 pi r times arc length gives us surface area. So if we didn't have the 2 pi r, we would be getting arc length. All right, so there's where we have our setup. We can do one more thing. Oh, what about limits of integration? If we're integrating with respect to y, we should be looking at the y-axis.
Like 0 to infinity?
0 to 2.
0 to 2.
2.
So we want to look at the curve that we're rotating. This curve stops right here. So if this curve continued on and we
Oh,
weren't
it just stops there. Okay.
yeah, it's stopping right there. So if it was going on forever, we would have an improper integral and we could go to infinity. But if we're going to stop right there, we look at the y-coordinate of that high point. That y-coordinate is 2. So we'll go 0 to 2. So 0 to 2. And then we have a one simplification step here. We're going to have 1 plus 4y squared in here. So that's our setup. On the exam, this will be integrable. This will be integrable. And there's a chance this is integrable with u substitution. Normally, when we look at something like this, what we're hoping is that the derivative of the inside of the square root is right there. Now, that's not the case here because the derivative of the inside is 8y, and this is a y squared. There's a chance if we let u be what's in here, we could rearrange it and somehow maybe do it, but probably not. This is probably not integrable. So on the exam, the derivative of the inside here should match on the outside so you can integrate it. So that's our setup though. Is there any piece of the setup that you are not sure about? Let's take a secondary look at this. Let's rotate. This one ended up being a dy just like the other one. Let's do this around the x-axis also just to see if we can see the setup. See how it changes. So let's take the same exact thing and let's rotate instead around the other axis, and let's just make sure we can still do the setup. So we're going to take axis of rotation there, and for our curve, same setup. That'll be at 2, this will be at 4, but this time let's go around x. So, same scenario. If we pick a point right here and come on down, that's going to be your R value. And your generic formula, we always like to draw the generic formula out. So the generic formula is the integral of 2 pi r ds. And we don't have limits with respect to s, so we just use stars or whatever. This function is y equals square root of x. And when we come in here, the 2 pi obviously comes to the front. R, all right. So we have essentially a vertical element, right? There's your R, that's vertical. This is at a random x. So what's the R value there?
Square root of x?
Square root of x. Yeah, it's the y value. The y value up here is root x. And this all is tracking. We've got a vertical element, so we should have a dx. So we're integrating with respect to x. So that R becomes square root x. Now ds is going to be a little different. We're going to use this ds. We're going to use the ds that has a dx out there. So we're going to have the square root of 1 plus y prime squared. Let's come over here and find y prime. Y prime will be 1/2 x to the negative 1/2. So 1/2 x to the negative 1/2 is 1 over 2 root x. And that's going to come in here and we're going to square it. So this will be 1 over 2 square root x quantity squared dx. Limits of integration. What do you think?
0 to 4.
Just the way.
Yeah, 0 to 4. So we're integrating with respect to x, so our limits should be coming from the x-axis. And so when we look here, we have a circumference for all of the x's between 0 to 4. There's a circumference that creates a length, and we're adding all those together. All right, now let's do a simplification step here, see if we get something that's possibly integrable. We don't know. When you just make stuff up, whether it's integrable or not is, who knows. So we're going to have x is going to come to the inside. So I'm combining the two square roots. It's going to come to the inside into both terms. This term is 1 divided by 4x. Everyone agree with that? When you square this, you have 1 over 2 squared, and root x squared, so you have 1 over 4x, and then this x is going to be distributed to both. So this actually simplifies very nicely. That x cancels, so we're going to end up with x plus a fourth. And is that integrable?
Yes.
That is integrable. We can just do it as we normally would a power rule. We have x plus 1/4 raised to the half power, so let's just do what we normally do a power rule. We would x to the 1/4 to the 3 halves, adding 1 to the exponent. divide by the new exponent. Dividing by 3/2 means multiplying by 2/3. And then we would have to do RCR. But the derivative of this inside is just 1. So dividing by 1, we can't see it. Doesn't appear. And then we have 0 to 4. So we have 4 pi divided by 3 as our coefficient. And then we're going to plug in 4 right there. So 4 plus a fourth. 4 plus a fourth is 17 fourths? Right? Did I say that right?
Yes.
17 fourths? Thank you. And that's raised to the 3/2 power. And then we have to subtract off what happens at 0. Plug in 0, we get 1/4 to the 3/2 power. And that would be our surface area. We could do a little bit of simplification here. Let's not get carried away, though, doing the arithmetic right now. If you have any confusion about how you might be able to simplify this, we can talk about it. The square root of 4 is 2, so you could do some things. And we've seen that if you have something to a 3/2 power, you don't absolutely have to do this, but if you want to be complete, that's how you would deal with the 3/2 power. Write it that way. All right, let's go to the next one. So that's 2. Work emptying a tank. Oh, I remember those. Do you?
ADD volume.
Yeah! Wow. Very good. All right, so what kind of tank do we want? So the simplest is the cylindrical tank. The hardest is that parabolic type thing, or the trough looking thing. I'm not going to give you the trough. That one's just a little too much work for final exam. So a cone or a cylinder make the most sense.
Okay.
Or a parabolic cylinder, no, it's not really. If you call it a paraboloid, that's also not too hard.
I don't know my area equation for parabolic cone.
Well, you don't need to know the area. Should we do a cone or should we do a paraboloid?
If we're doing work, isn't it volume?
Yeah, I'll show you though why we don't need to know it. Cone. Let's do a cone. Okay, so let's do a cone. So if we've got this shape right there, and it's filled with, we'll just go with water. There could be a different liquid that has different density, but we're just going to go with water. So we have two choices. It can either be drained out the bottom, right out that vertex, which means gravity's doing the work, or it's pumped out the top, and usually we're just going to pump it right out the top. We could add a pipe to it if we wanted to, but if we're just going to go up to the top, then it's different. The distance traveled by each slice of water would be different if we had a pipe out the top. So let's suppose that we're dealing with, let's suppose that the height of our cone is 6 meters. Okay? And let's suppose that the radius right here is 2 meters. And we want to find the work done in emptying it right out the top. So if we look at a cross-section, so cross-section is two-dimensional. So there is a cross-section of water. This we do need to know the area of. We need to know the area of that cross-section. That's just a circle. So if we did have a parabolic shape, the cross-section is still a circle. Whether the tank is cylindrical or conical or parabolic, the cross-section is going to be a disk. Okay, so this is going to be the cross-section at y. And what is the area right there? So by r squared, we need to figure out what this r is here. So I've used r to represent two things here. That's always a little dangerous. Let's make this a capital R just to keep it separate. Or what I could do is this to make it a little bit easier. let's just not put that R there and just put that as 2 meters right there. That's probably easiest. Okay, so we have to find R as a function of X or a function of Y. Which one?
Function of X. Function of Y.
Function of Y.
Function.
Because like, think about aren't your cross sections at different Y's?
Yeah.
Right? You want to know what the area of that disk is at a height of Y. Right? When we say that this is the cross section at Y, that tells us that we're trying to find everything as a function of Y. We want to know what is the area if we're at a height of 2? What is the area if we're at a height of 4? So it's Y is going to act as the independent variable. Okay. So to figure out this R, we need to know what the equation of this diagonal line is. Right? That R is going to be a horizontal distance based on this diagonal line. So we would need to be able to find the X value for that diagonal line, which would be in terms of Y. All right, so what is that Y? What is this function right here? Y equals
3x.
So we're going to go up 6 over 2. So y equals 3x. So now we have this diagonal line written as a y value. If we want this black radius, that's a horizontal distance. So that means, OK, let's rewrite this function as an x value. So let's isolate x so that it's measuring horizontal. And whenever we have a function, we can either think of it as measuring vertical or horizontal. If we have y isolated, it's measuring vertical based on x. If we have x isolated, it's measuring horizontal based on y. So now that's measuring sideways. That is our radius. So the area is pi times y over 3 quantity squared. So we get pi y squared over 9. That is the area of the disk at height y. If you plug in 0, your disk has area 0. If you plug in a y value all the way up at the top, that y value would be 6 all the way to the top. Plug in 6 there, 36 divided by 9 is 4. 4 times pi would be the area of the disk at the top. And that tracks because the area of a circle of radius 2 is 2 pi r, which would be 2 times 2 pi, which is 4 pi. So this area formula tracks. If you test your two extremities, you get the right answer, you probably have the right area function. OK, now we wanted work. So work, the acronym that we've been using is ADD volume. And we put the volume in parentheses because that's supposed to be a cue that it's not the volume of the whole tank. It's the volume of a slice. And if we think about this cross-section of water, that's two-dimensional. But as soon as we add some thickness to it, now we have a volume. And that's the volume that we're talking about in the parentheses. So we're trying to find the volume of that little puck of water in this case. So how about limits of integration? 0 to 6. We're measuring vertical. We're adding the work to pump each layer or slice of water out the top. So we have slices of water between 0 and 6. And then ADD. Acceleration due to gravity, 9.8. So 9.8. Acceleration density. So whatever the fluid is, in this case, we're dealing with water. So the density of water is 1,000. If we were dealing with beer or something else, whatever the density of that liquid is, we put that in. So that has to be known. So that's given to you. So acceleration, density, depth, or usually we think distance in this case because that slice of water is being pumped out the top. So we're thinking about how far it travels, but that's equivalent to how deep it is. So that depth part, the second D is this. And what is that distance?
Y minus
6 minus 1.
6 minus y.
6 minus 1.
because y is below 6, right? Y is smaller than 6 because it's below it. So if you want to see that, if you think about distances, all the way there is 6, and then this distance here to here is y. So that distance is 6 minus y. So 6 minus y will be, so there's our ADD. That is our ADD. Yep.
For the test, should we know that density of water is 1,000?
I'll give it to you.
You'll give it to us.
Yeah, I'll give it to you. So there's the ADD. Now we want the volume of our puck right there, the volume of that slice of water. Well, it's the area multiplied by dy. That is the volume. So area right there, pi y squared over 9 multiplied by dy. So this right there is volume. Area times thickness gives us volume. Cross-sectional area is two-dimensional, and then we multiply by thickness, and now we have a tiny volume, a volumette. And then we have to multiply this all out and integrate with respect to y. The setup is the most complicated part of the problem, though. Should be. Is there any part of the setup that you want to ask about? Everyone see the 6 minus y piece? Everyone see the pi r squared piece? Everyone see why we have to isolate x right there? Because that disk has a horizontal radius. So we have to take our function that's building that horizontal radius and isolate the x so that it's measuring sideways instead of up, down. All right, that is work. Question?
Will you ask for correct units with work?
Yes.
And that would be joules?
Joules.
Joules.
Yeah, so work is joules and force is newtons.
Newtons.
Yep. Yep.
But since it says on your test prep we're doing work, we just have to remember work.
That's all you have to remember. So little. This should be easy. Okay, let's look at number 4. Hyperbolic, derivative and integral. So let's take the derivative with respect to x of, let's do 4 tanh 2x. Well, let's just do that first. Let's do one that's just pretty straightforward derivative. A very straightforward derivative. If you remember your derivatives. Okay, so when we think about these hyperbolics, they're called hyperbolic trig functions because they mimic what the trig functions do. And we have parallel derivatives. The one big change is that the derivative of sinh and cosh are each other. Right? So one thing we could do if we forgot the derivative of tanh, we could just build it. We could do sinh over cosh and use the quotient rule because we know the derivative of sinh is cosh and vice versa. So we could build it if we totally forgot. But if we think about the trig functions, what's the derivative of tangent?
Secant squared.
So derivative of tangent is secant squared of x. So this is going to be parallel to that. And what we said as one of the cues is that the derivative of sinh, cosh, and tanh, those are all positive, and then the derivatives of the others are negative. So derivative of sinh, cosh, and tanh are all positive. So this is going to be 4 sech squared of 2x multiplied by 2. So this would be 8 hyperbolic secant squared of 2x. That would be the derivative there. That make sense? Okay, so let's try a more complicated one. Let's suppose we have the square root of 2 cosh 3x. And suppose we want to take the derivative there. So it's very similar to differentiating cosine. So if we're going to differentiate this, we're going to pull the 1/2 down in front, so 1/2 comes down. And then we have the inside raised to what power? Negative 1/2. So power rule, half down, inside, which we often call the base. Subtract 1 from the exponent. And then we have to multiply by
The derivative of cosh.
the derivative of the inside. And what's the derivative of the inside?
Since
Sinch
dx.
3x times 3.
Yeah. What you all were saying. Derivative of cosh is sinh, derivative of sinh is cosh. So inside here, we'll have a chain rule. We have to bring the 3, multiply it by the front. So we'll have that. So if we want to simplify all this, we're going to end up with 6 sinh of 3x. And then in the denominator, we're going to have a 2 from this 2 here, which we'll simplify even more in a moment. And then this is going to be the square root of 2 cosh 3x. And then the only simplification that is obvious is that. Yeah?
Do we have to simplify to get all points?
Yes.
Oh, no.
Yeah. Oh, yeah, yes, you have to simplify. You don't ask for, can I have 2/4 of a cup of flour when you go to the store? You do that?
Sometimes.
And do they look at you funny?
No.
Yeah, simplify whenever you can. Okay, let's do a couple integrals. So classic integral would be sort of something like this. What if we have that? Hint, use substitution. All right, what are we going to pick for you?
Sine.
Cosh.
Cosh. Do you agree? I agree. I heard someone say sinh. All right, so if we pick cosh, the whole idea is that we want to pick the one with the higher power here, because when we take the derivative of cosh, then we get its derivative right over here on the side. So if we pick cosh, the derivative is sinh. So we'll have du equals sinh x dx. And sometimes with terminology, I'm just thinking about what Sam said earlier. This, we actually have taken the differential of both sides. Like if somebody said the derivative here, you would say that u prime is sinh. Well, u prime is du dx would be sinh. And when we're doing substitution, there's the derivative, but then we rewrite it as a differential and not as a derivative. But, so FYI. So then this is going to be u to the 5th times du, which is u to the 6 over 6 plus a constant of integration. And then we back substitute, and we will end up with 1/6 multiplied by the cosh of x raised to the 6th power plus a constant of integration. And that would be our antiderivative. All right, some cobwebs are getting blown out of your head. Hyperbolics. And remember that the hyperbolic cosine is the hanging cable. So that's the one that goes through the point 0, 1. And then sinh is the one that looks a lot like a tangent, and it goes right through the origin. And usually we don't ever ask anyone to think of the graph of any of the other hyperbolics. Those two are the most important. Cosh, hanging cable, the most important. All right, number 5. Number 5 is, wrong page. Number 5 is integrating products of powers of trig functions. Oh, we actually just kind of did that. So so that one parallels what we would do if we had powers of sine and cosine. Let's do secants and tangents. So number 5, well, let's suppose we have, let's suppose we have secant raised to the 4th power multiplied by tangent raised to the 3rd power. So this one could be done in 2 different ways. One way is better than the other. So the piece that we have to remember is that if secant is to an even power, we're going to pull off a secant squared and convert the leftovers to tangent. The concept being that if we let u be tangent, the derivative is secant squared, so what we pulled off will match. It will be the derivative of what we choose for u. If we think about pulling off a tangent, we're not only just pulling off tangent, we're pulling off secant tangent, because the derivative of secant is secant tangent. And so then the idea would be we're going to let u be secant, and everything remaining has to be secant, so we let u be secant, and then du is that sectan. So in this case, we could do either. So let's just set it up with both cases just to be thorough. Do you see which one's going to be easier? Actually, in my mind, when I created the problem, I thought one way would be easier than the other. But now that I'm looking at it more carefully, they're going to be about the same. Because if we pull off a sec tan, we have to convert tan squared. And if we pull off a sec squared, we have to convert secant squared. So they actually are going to be about the same difficulty, because we're converting a square in both cases. Generally, whichever one has the higher power, that's the harder one to convert. So you usually go with the lower one. In this case, it's not going to matter. So let's write it both ways. So if we see if it jumps out at us that we want to pull off a secant squared, so we've pulled that off, so that's going to be, the concept then is that we're going to let u be tangent, because tangent's derivative is going to grab that secant squared at the end. So these are what in class we've been calling the leftovers. We pulled off 2 secants. These ones were left behind. So these need to be converted over to tangents. So then we can let u be tangent, and everything in front is tangents. So how do we convert secant squared to tangents? What's the identity?
Tan squared x plus 1 equals secant squared.
Exactly. Exactly. So that's our, that's not a square up there. So this is our triangle. That's the triangle that shows us. And so that secant squared is going to be 1 plus tan squared. So that's going to go right out in front here, 1 plus tan squared. We're using x's. And now we're good to go with u equals tangent. So if we come off to the side and let u be tangent, du is secant squared of x dx. And that will turn this into 1 plus u squared times u cubed times du. Distribute the u to the 3, power rule it for integration, and then back substitute tangents in for all the u's. Everyone get the finish line on that? Distribute, integrate with respect to u. So let's take a look at that second option here. So, or if we were more inclined, we could have pulled off a secant multiplied by tangent. So then we would have secant cubed tangent squared. So we're pulling off one of each. So then over here we have a secant x tangent x times dx. So secant x tangent x dx. So in this case, we want to let u be secant because the derivative of secant is secant tangent. Oh, it's time for a break. So which ones are the leftovers here? Those are the leftovers. Those are the ones that we want to convert. Because the concept here is that if we let u be secant, then there's the derivative. So all these have to be secants. So we're going to convert that over to secants. So we'll have secant cubed of x multiplied by tan squared. We look at our triangle, that's going to be secant squared minus 1. And then we are good to go. Now we can let u be secant, and du will be secant tangent. And our substitution is going to yield that. And then we're in the same position. Distribute the u's, just like we did there. Integrate with respect to u, and then back substitute where all the u's get converted back to secants. And these are going to look different. One will have secants, one will have tangents, but they will be equivalent. All right, let's take a 10-minute break. Let's take a tiny break.
Want to see some intensive writing?
I want to see some intensive writing, yeah. Let's see it.
It's just the integration.
Question? Trig sub. Trigonometric substitution. Everyone's favorite. So let's suppose we have this integral right here, and we want to use trigonometric substitution to evaluate it. The first thing we have to figure out or remember is whether we use sine, secant, or tangent. Those are the three, sine, secant, or tangent. And only one of them is going to make an identity down here that makes sense. The other two are going to create square roots of negatives or something that can't work. So only one will work. And we know that when it's a plus, we use tangent. So now we have to remember, is it sine or secant? Sine. And then we use sine because 1 minus sine squared is cosine squared. That's the one that's an identity. 1 minus sine squared. 1 minus secant squared is negative tangent squared, which is a problem, because then we'd have to take a square root of a negative. So the only one that's going to work is sine. So that's our target. Now, before we actually do that substitution, we would like this to be a difference of squares with a leading 1 instead of a 4. That makes our life a lot easier in the long run. So we are going to factor out that 4. When we factor out that 4, it's coming out of a quantity that's raised to the 3/2 power. So that 3/2 power is attached to that 4 as it comes to the outside. So that's going to be 4 raised to the 3/2 power. And then inside here, there is no 4 with the x squared, so when we pull out the 4, it puts a 4 in the denominator. And one way to think about that is that you've multiplied by 4 over 4, and that 4 in the numerator is coming out and creating that 4. So what's left is x squared over 4, and we want to do one rewrite there. We want to make that x divided by 2 quantity squared. So then we have that. Now we're ready for our sine. So we're going to let x divided by 2 be sine of theta. And then we're going to take the derivative or the differential, however you want to think about it. Got that. Now we're ready to convert all the x's over to thetas. So out in front, we'll simplify that constant. 3 over 2 as a power, 2 is the root, so we'll do that first. The square root of 4 is 2, 2 cubed is 8, so we'll have 1/8 out in front. And now x cubed. From this equation, we see that x is going to be 2 sine of theta, And if we cube it, we're going to get 8 sine cubed of theta. So that's x. That's the x cubed part. Now dx. We look down here for dx. That's going to be 2 cosine of theta d theta. So dx is all of this. X cubed is that. And then down below, we have 1 minus sine squared raised to the 3/2 power. So there's our main setup. Any questions on any of those stages? The stages of integration. Paralleling the stages of grief. So we will have, I see a 2 coming out in front. The 8s are canceling. So those cancel, we have the 2. And we will have sine cubed times cosine. And then down below, the whole point of picking sine is that this becomes an identity. 1 minus sine squared is cosine squared. Cosine squared to the 3/2 is cosine cubed. So that's our next step. All right. Now a cosine will cancel. And we've got sine cubed over cosine squared. Okay, so we have a couple choices here. We see that the power on sine is odd. And we had a rule that if the power on sine is odd, we can pull one off and convert the leftovers to cosine. So let's see if that helps us. So if we pull off one sine, put it over here with the differential, we're left with a cosine squared, which is, we're left with a sine squared, which is 1 minus cosine squared. Ugh. Doesn't sound good. So we have that. So then we would let u be cosine. Let's see if we'll go one more step, see where it takes us. And you just make up questions out of thin air. Some strange things might happen. We'll see. Okay, so we have 2. Now we're letting u be cosine, so we have 1 minus u squared divided by u squared. That's okay, we like that. And then sine theta d theta is negative du. So we'll put a negative in front, put a negative in front, and a du right there. That's not too bad. That actually is, if we split this fraction, we're kind of okay. That's going to be u to the negative 2 minus 1. So this will be negative 2, and then add 1 to the exponent, divide by the new exponent. So negative 1 over u. And then minus u. And then plus c. We've got a couple back substitutions here. All right. So let's go ahead and at least distribute the minus. Let's distribute the whole negative 2. So we're going to have 2 divided by u, so that's 2 over cosine of theta. And then we're going to have plus 2u, so plus 2 cosine theta, plus c. So there is our integration with respect to theta. We now have our antiderivative with respect to theta. We need to go all the way back to x. So to get back to x, we have to build our triangle, or triangle that takes us between x's and thetas. And when we look up here, this tells us how to build our right triangle. We always build it like it's sitting in quadrant 1 of a unit circle. And that says sine of theta is x over 2. So sine is opposite over hypotenuse. It has to be x over 2. That allows us to get the third side. That will be the square root of
4 minus x squared.
4 minus x squared. Hypotenuse squared minus other side squared.
Um,
Yeah.
when we integrated 1, do we not just get theta, not u?
So here we get u. Here we're integrating with respect to u.
Okay,
So we'll get u, and then when we substitute back, it turns into a cosine.
okay.
But we haven't, but we're not integrating that one. So the integration happens with respect to u.
But that 1 becomes a u, not a theta.
Yes,
Okay.
it becomes a u. Correct. Yeah, we're integrating this piece with respect to u, so it becomes a u. But then it becomes a theta after we let u turn back into cosine.
Okay.
And then when we look at that triangle, what we see here is that cosine is the square root expression divided by 2. So when we go to change it back, here we have 1 over cosine, which is secant, so we could do 2 over that. So we're going to get 4 over that square root expression, plus 2 times cosine. Cosine is the square root over 2, so that will give us just the square root expression, plus c. So there is our antiderivative, when all is said and done.
Thank you for not making us rationalize the denominator.
Yeah, you don't have to rationalize that denominator. All right, so questions. Trig sub's always such a meandering thing.
Sometimes they're easy, sometimes not.
That one wasn't, that wasn't too crazy. I don't Doesn't seem too crazy? All right, any part of that you want to go over? Is it hopefully making sense by now? All right. Full test, trig sub. All right, number 7. Ooh, improper integration. Another favorite.
Let's go.
Let's go. Improper integration. So let's suppose, that was number 7?
Yeah.
7? Okay, improper integration. So the idea here is that we have unbounded area, and that unbounded area can be finite, or it could be infinite. So if we look at the simplest type of improper integral, we're actually going to see infinity. Good luck with your potluck. We're gonna see the infinity symbol right in the limit of integration. That's the most obvious improper integration. So let's suppose we have something like that. Is that going to be finite or infinite? We should actually know ahead of time. What was that? I heard you mumble something.
I think I just mumbled
That would be a p series where p equals 1/2.
So is it going to be finite or infinite?
That would be infinite.
Yeah. We will see that this is going to be infinite. Now, it's super important on the exam, you have to make sure that you use limit. So this is going to be the limit as b goes to infinity, or whatever your favorite letter is. So we first are going to convert it to a definite integral. So that's what it would look like as a definite integral. So it's the limit of a definite integral. And we keep on keeping on with the limit. We add 1 to the exponent. We divide by the new exponent. And we have our limits of integration here. So don't forget your limits of integration. So that 1/2 in the denominator becomes a 2 in the numerator, and we can factor it out to the front if we like. And then we're going to plug in our limits of integration to the x. So we're going to have the square root of b minus the square root of 1. The square root of 1 is 1. And this limit is as b goes to infinity. And what is that limit?
Infinity?
Infinity. And square root of x goes to infinity. If you subtract 1, you're still dealing with going to infinity. Multiply by 2, we're still going to infinity. So this tells us that the area is infinite. So if we were to look at a graph of this function, it looks like all these graphs that we've looked at. They're all doing this kind of thing. Right, as x goes to infinity, the denominator goes to infinity, so the fraction goes to 0, horizontal asymptote at the x-axis. But this is just not going to the x-axis fast enough. So this is going to the x-axis for sure, so it's like that inconclusive divergence test. The terms are going to 0, they're just not going to 0 fast enough. If we have another type of integral, let's suppose we have 1 over, and let's suppose we are going from 0 to 4. Well, let's take a look at this. Yeah, let's go ahead and go with this. So, do you see that it's improper? So it's not obvious because you see an infinity symbol, but it should be semi-obvious that if you plug in 4, you have a vertical asymptote. So that's how we see that it's improper. So we need to introduce a limit. And so whatever letter we want to use, were they using C for the middle? I think. Does not matter what letter. So we're going to go to 4. But what side of 4 are we going to approach it from?
The left.
The left side. We have to stay within our interval. The interval is from 0 to 4, so we have to be inside the interval from 0 to 4. So as we're getting closer and closer to 4, it's from the left side. So we need to put a little minus up there to indicate this. And we're going to go from 0 to c. And then let's write this as x minus 4 to the negative 2 dx. Now we have a definite integral. So limit, we can do this integration now. We add 1 to the exponent, divide by the new exponent. So when we do that, we end up with this. So adding 1 gives a negative 1, dividing by negative 1. We can pull the negative 1 out if we want. It does not matter. Let's just leave it in this time. So we will have limit as c goes to 4, not infinity. So we plug in our c. We get negative 1 over c minus 4. Minus a minus is plus. And then we're plugging in 0. So we have 1 over negative 4. Okay? Now, what happens when we plug in this 4 here? We plug it in this denominator, and we see we have a 0 in the denominator. So the question is, what does this approach as we get closer and closer to 4 from the left-hand side? What's happening to this whole fraction here? Is it going, including this minus in the numerator, is the whole thing going to negative infinity? Is it going to positive infinity? Or is it going to a constant?
Negative infinity.
So if we plug in a 4 coming from the left, think about 3.9. 3.9 minus 4 is negative.
So positive.
Negative and negative is going to make positive. So this will actually go to positive infinity. All right. And then positive infinity minus a fourth is still positive infinity, so this is going to be infinite. So that is also going to diverge. And that illustrates our two principles, that if you're dealing with a horizontally unbounded region, so under that, that slope down there, the power has to be bigger than 1. But if we're dealing with a vertically unbounded region, to get convergence, the power in the denominator has to be less than 1. So for vertical convergence, less than 1. Right? Horizontal convergence, greater than 1. So we had that summary slide when we were doing these improper integrals. Okay, so that one is also going to diverge. Well, let's take a look at something else on our. So that was 7. Integration by parts. Integration by parts. All right, let's do an integration by parts. So if we have something like, that. Oh, that's not a good integration by parts because we can actually do that with just substitution. Let's make this more complicated where we have to use integration by parts. Let's make it, does anyone have one close at hand, integration by parts?
Like x times x squared plus 1?
Yeah.
Times x squared plus 1?
So if we can,
Or you need to put like a number.
yeah, we want to do something where we can't do it in a simpler way. So let's do something like x ln x. That we can't do in a simpler way. So if we have something like that. So the classic integration by parts is to deal with products. And so there we have a product. And we don't have a u substitution that's going to work really easily. If we let u be natural log, the derivative isn't there. If we let u be x, the derivative isn't there. So that'll definitely work. X ln x. OK. So when we do integration by parts, we set up our integration by parts table. And we can pick several different options in many cases. Sometimes you can't. And now in a case like this, the general rule of thumb is for dv to pick the biggest piece, the biggest factor that you can easily integrate. When we look up here, we only have two factors. We have x and we have ln x. So one of them has to go with the dv. Putting ln x with dv doesn't make sense because we don't know an immediate antiderivative for natural log of x, most likely. Some of you may know it by now, but that's not an easy antiderivative. So this is the most natural thing to do. Then we take a derivative in the left column and an integral in the right column. So the derivative in the left column is du equals 1 over x dx. The integral in the right column is x squared over 2. And this is x dx over here. So the dx always has to go with the dv. And that is going to be our integration by parts table. And then we do the ultraviolet voodoo part. So ultraviolet voodoo, UV is the ultraviolet. So we have 1/2 multiplied by x squared multiplied by ln x. UV minus the integral of v du. And what we notice is that v multiplied by du, we're going to have an x that cancels, so we're going to end up with x divided by 2. So uv is this main diagonal, and then we subtract off the bottom row. That is easily integrable, so we are on the right track. So we have 1/2 x squared natural log of x minus x squared divided by 4 plus c. That'll be our thing. And then the other integration by parts that we had was the integration by parts with a twist. And the integration by parts with a twist was when we had both functions having circular derivatives. So the integration by parts with a twist, we have something like e to the 2x multiplied by sine or cosine. So if we have something like that, that we would do integration by parts with a twist. Should we go through this one? I'm seeing some yeses. So you're going to end up doing, you know you have twist when both functions have derivatives that sort of cycle through the same function repeatedly. The derivative of an exponential continues to be an exponential. The derivative of cosine turns to sine, but then back to cosine. Turns to sine, then back to cosine. So it's circular in nature, though. And it's not going to matter which we choose for u and which we choose for dv. I'll just do it in the order that it's presented. So here would be the first row of our integration by parts table. And then the first column we're differentiating, so du will be 2e to the 2x times dx. Here we're integrating, so we'll have sine of x. And notice that normally when we integrate, we have a plus c. With integration by parts, it suffices to always choose a 0 as your constant of integration. It does not matter. It would disappear in the long run if you decided to be a contrarian and put a plus pi or something. All right, so now we have uv. So that's going to be e to the 2x sine of x, uv, minus the integral of v du, that's the bottom row, 2e to the 2x multiplied by sine of x dx. And here's where we start to notice this twist thing about to happen. We often ask at this stage if the integral is easier than the original, and here we see that it's comparable. It's not easier, it's not harder. It's still a trig function times e to the 2x. And so when we do our second integration by parts, you have a couple choices. The first is that you really need to stick with the same pattern that you did originally. If you let u be the exponential originally, you need to continue to do that. Okay. Next thing is this constant. Yes, you could factor out the 2 to the front. If you factor out the 2 to the front, you just have to be careful with the big set of brackets because that 2 will have to distribute later. Third thing is that it's easiest if you have a plus in front. Because even with the minus, you still have the minus with the big brackets that's going to have to be distributed. The simplest way to get this to work out nicely would be actually to make this plus and move that minus inside. Then it just sort of eliminates the need for distribution in the end, and it's just all going to be expanded with no distribution. So I'm going to do that. I'm just going to move the minus inside. And for u, we'll choose negative 2e to the 2x. And then for dv, we choose sine x dx. Differentiating here, we have du equals negative 4e to the 2x dx, and v equals negative cosine x. All right, so on the right-hand side, we've got our coefficient function out there, our leading function out there. Now we do integration by parts again. So uv, main diagonal, looks like it's going to turn positive, so we'll have 2e to the 2x multiplied by cosine x. uv minus the integral of v du. All right, that's not too bad because this now becomes positive. So we'll have 4e to the 2x cosine x. And so here is where we usually say, that matches. Let's call the original integral something. So let's call the original integral omega. So that means that omega is equal to this whole thing. And what we notice is that we have a multiple of omega over here. So this coefficient stuff, or maybe I shouldn't say coefficient, this leading stuff will still be there, and then we have minus 4 omega. If we call omega the integral of e to the 2x cosine x, then we have 4 of them over there. So there, we've gotten rid of the integration piece. Now we do the twist part. We're going to twist those omegas together. So we're going to have 5 omega. 5 omega is going to be equal to this stuff here. And that is going to look like this. One caveat, as soon as we twist our omegas, we need a plus c on this side. Because this side has a built-in constant of integration kind of hiding in the wings, waiting. And so when we move the omega over there, we've got to make sure we put a plus c as our constant of integration. And what's our final step? Yep, divide by 5. So dividing by 5 will give us our final answer. There we go. And c divided by 5, we're just going to treat it as c. So this will be our final general antiderivative. Integration by parts with the twist. Just for fun. All right, so that was whatever it was. Integration by parts. All right, geometric series. Okay. Exam 3, 9 to 12. So geometric series, alternating series remainder, IOC, binomial series expansion. Let's do geometric series. I think we have plenty of time. I think we can get through all those maybe. So geometric series, was it 10? 9. Okay. Oh, 9 to 12. Yeah, 10 is next. So geometric series, the classic, there's always, they're trying to obfuscate. So let's just suppose we have something like this. Let's suppose we have 5 to the k plus 1 divided by 6 to the k minus 1. What we would like is to have exponents that are just k and not with this extra constant mumbo jumbo. And so the key for these is to just see that you can use laws of exponents to rewrite this. This is 5 to the k multiplied by 5. This is 6 to the k multiplied by 6 to the negative 1. And we just want to get rid of the constants that are coefficient constants. And so this, if we do one more step before we do any factoring out, does everybody see that that's what we have? That 6 to the negative 1 just pops the 6 to the top. The 5 just stays there. So when all is said and done, we are dealing with 30 coming out to the front. And our series then can be rewritten in a geometric form. Now we can identify the important pieces of this geometric series. There are two important pieces, A and R. For a geometric series, we want to know the initial term, and we want to know the common ratio. And what is the, and here we need to be a little thoughtful. You can treat this part separately. This is a series. And when the question says, what is the sum of the entire series? we would have to multiply by 30 in the end. But if we want to focus in on just this geometric series piece of it, let's just focus in on this. Let's forget about the 30 for a minute. So what is A for this series part, the part boxed in blue?
5, 6.
5 over 6. And what about R?
5, 6.
5 over 6. Okay, so now when we find the sum of the entire thing, that's going to be 30, for sure out in front as a multiplier, multiplied by A over 1 minus R. So then,
R is less than 1.
and great point. This R value is less than 1, therefore we have convergence. So it makes sense to go to this step. If that R value were not less than 1, it makes no sense to go to this S value. Even though technically you can compute it, A divided by 1 minus R, you can compute it because every geometric series has an A and an R, but it only makes sense if the series actually converges. And then if we multiply up and down by 6, we'll have that. So we get a total sum of 150. So geometric series, probably the most important series. Any issues with the laws of exponents or solving it, finding S? Okay. And then after geometric series, we have alternating series remainder. So, alternating series are the one type of series that we are looking at remainders in detail. There are a whole bunch of other options for series that aren't alternating, but for us, that's the only one we're going to look at carefully. They have a formula for Taylor's remainder theorem, which we're not going to deal with. So let's suppose we have an alternating series. Let's suppose it starts at 3, goes to infinity. And let's suppose we have minus 1 to the k plus 1. So the first term's positive. And let's suppose we have 1 over k squared. So we have an alternating series of 1 over k squared. And the question says, how many terms, so number of terms, for the remainder to be less than 1 over 10 to the 4th. All right, there's two standard ways to do it. The way I like to do this is to think in my head that as soon as we have a term less than the prescribed error, we add everything in front. So if we can find the term that's smaller than the error, then we add everything that's in front of it. So this first step then, in my mind, is that I want to know the k that corresponds to the term that's less than the prescribed error. So we want to know, when is this less than 1 over 10 to the 4th? That's what we want to know. When is it? What's that k value? And it's strictly less than, not less than or equal to. All right, so then cross multiply, and 10 raised to the 4th power is that. That's k squared on the right, cross multiplication. We can take the square root of both sides. K is bigger than 100. So that says that when k is 101 or greater, all of those terms will have magnitudes less than 10 to the negative 4. So if we want the smallest k bigger than 100, we're going to choose k equals 101. That is the smallest k bigger than 101, bigger than 100.
But don't you have to take into account that k equals 3?
We haven't gotten there yet.
Oh,
That's the next step. So this is pure math here. We just say, hey, when is this going to be less than 10 to the negative 4? It's going to be less than 10 to the negative 4 when you plug in a 101 right there. So that is the first step, finding k. The next step is the little straddle to figure out, okay, well, if k starts at 3, what does this mean? So, and here you can do it in several different ways. I like thinking of it this way. So if when k is 101, that's when this is less than 10 to the negative 4. So we want to add all terms in front of k equals 101. So we want to add everything in front, all the k's before 101. So in other words, we want to add from k equals 3 up to k equals 100. That's what we want to add together. We want to add all this stuff. So if we add all this stuff, if we add all this together, we will have an answer that's within 10 to the negative 4 of the actual sum of the full series. And so now here's where we have to do our little finagling. How many terms is that?
98.
98 terms. And so here, there's a couple of ways to do it. You can say, okay, well, if this case started at 1, that number up there would tell us exactly how many terms we were adding together. To make that a 1, you subtract 2. So then you subtract 2 up there, and you have 98 terms. Or you could say upper minus lower plus 1. That will also work. 100 minus 3 is 97. Add 1, you get 98. So whichever works best for you. So it's just, as long as it's clear in your mind that if you're going from k equals 1 to 5, whatever this happens to be, this is 5 terms. If that counter starts at 1, that upper number tells you exactly how many terms you're adding together. And so using that little algorithm there, make that a 1 by subtracting 2, then you do the same thing to that up there. That's the easiest way. Okay, so that is alternating series, remainder. Integral of convergence for a power series. So, let's see. So we've got a power series. So a power series is a series of powers of x. So that means that on the far right side, we should be seeing things like x squared, x cubed, x to the 4th, not x squared plus 1 to the cube or something. It's got to be x raised to powers. There can be some missing, x squared, x to the 4th, x to the 6th, but it's got to be powers of x. Not power, and it could be powers of x minus 5 or powers of x plus 3, but you can't have an x squared inside parentheses, which we saw in the last test. So let's suppose we have a power series. So let's suppose we have, let's go with something like x to the k divided by the square root of k. Let's do something like that first. So k will start at 1, go to infinity. So that is a power series. Now, a lot of times we will, but you do not have to. Sometimes some books will emphasize that you always want your x to the k kind of pulled off to the side, and you're thinking of the other parts as coefficients. Does not matter. You see it written in both ways. Just like with integration, it would be ideal if we always had the dx off to the side, but we get cramped for space, and we just don't do that. We'll do that instead. It'd be nice if we were always really consistent and had the integral and the dx and then the function in the middle, but that's just not how life works. Okay, so we we've got that going. It's a power series. We need to know what x's it converges for, what x's it diverges for. So we're trying to find the interval of convergence. And we don't know right now. We use the ratio or the root test. The root test is only good for a power series if there's really a power on the far outside. If you were to take the kth root of that, yeah, sure, no problem. But then the kth root of this, the kth root of the square root of x of k, you can do it if you're careful, but my recommendation is just go with the root test only if there's a power on the outside of everything. So here we're going to go ratio test. So the ratio test says take the limit as k goes to infinity, and usually we call this an r. We call it an r. It should reflect geometric series, r less than 1 converge, greater than 1 diverge. Okay, so r equals the limit, and we do consecutive terms that look like that. So the term in the numerator is further out. So it should be a fraction. Should be smaller. So let's see what we get. So a sub k plus 1. Let's use this form up here. It's a little easier to do it in. So we're going to have x to the k plus 1 divided by the square root of k plus 1. Now this is absolute value. So we need to have absolute value around those x's. The denominator is never negative. It's positive square root. That symbol means the positive square root. So we don't need absolute values there. So there is a sub k plus 1 absolute value. Divide by a sub k means multiply by the reciprocal. And the reciprocal of this will be root k divided by x to the k. Again, x is a real number. And when k is odd, if you had a negative real number raised to an odd power, you'd have a negative. So we have to have the absolute value bars to wipe out the negatives. All right, let's simplify a little bit. So we have limit. There's one extra x up top. So we're going to end up with an absolute value of x. And then we've got the square root part here. And this limit is as k goes to infinity. The x can come to the front because there's no k in it. You're taking the limit as k goes to infinity. If there's no k in this part, that can factor to the front. And then we do this, turn it into 1 square root, take the limit as k goes to infinity. And let's just focus for a moment just on this part. What is the limit of that part? 1. If the limit can push inside, and we have k over k plus 1. Lots of ways to think about it. Divide everything by k. Highest powers are matching, so you take the coefficients. Whatever your method is. So this absolute value of x stays, and then this limit is 1. So we end up with the absolute value of x. That is the limit of the ratio of consecutive terms. Now we go geometric series, and we say, when is this less than 1? We want to know, when is that less than 1? Any x that gives us a ratio less than 1 will give us convergence. Any x that doesn't satisfy this inequality will give us divergence. All right, so this tells us then that x is between -1 and 1. We know that this means that our radius of convergence is 1. Whatever that number is, once you've isolated the absolute value, that's going to be a radius of convergence. Or you can look here and say, oh, this compound inequality, we have an interval 2 units long, half of it's 1. It's the radius. Now we have to find the IOC. So the IOC, we know the left and the right endpoint, but we just don't know what happens at -1 and 1. So now we have to test. So this is always the most tedious part. So we have to test x equals -1. We have to test x equals +1. So we come up here and look, and we're plugging in right there for the x. So the variable is x. That's the number that's the piece that can be changing. So we have -1 to the k divided by the square root of k. Plugging in for the x. So that's what we get. What kind of series is that?
Alternating.
Alternating. Is it converging or diverging?
Converge.
It's converging because the terms are going to 0 in magnitude. And that's all we need to know for an alternating series. If the terms are going to 0 and it's alternating, it converges. The alternating series test can be condensed down to that concept. If it's alternating and these terms are going to 0, it converges. So this is going to converge by AST. We don't have to show the steps when we're dealing with endpoint convergence. It's enough to just identify what the test is. So that tells us then that we have a bracket on the left. Now let's test +1. +1, we have 1 to the k, which is just 1. So we have that. What kind of series is that?
P series.
P series with p equal to 1/2. And converge or diverge? Diverge. So this is less than 1, therefore diverge. And P series converges if it's greater than 1. Less than or equal to 1, diverge. So there we have it. There is our IOC. There we have it. Now, then we have the couple of other concepts here. So once we have our power series with our interval of convergence, if you were to create another power series by differentiating this or integrating that, the interval of convergence would stay the same, but you would have to retest the endpoints. So if you take a derivative or an integral of a power series, the endpoints of the new interval will stay the same, but you might gain or lose convergence at the endpoints if you differentiate or integrate. Now, if there's substitution, the interval definitely changes, if there is substitution. Okay, so binomial series expansion. So binomial series. Let's suppose we have, like, let's go with this. Let's go with that. So for a binomial expansion, this thing down here is always a binomial. We've looked at it as powers of 1 plus x. That's how we build our generic binomial expansion. And in this case, the p-value, the power, is -3. And so our binomial expansion looks just like a geometric series, except that our coefficients are not standard coefficients, they're binomial coefficients. And let's go with 4 non-zero terms. But this is a series, so we should have the plus ... So there is the binomial series expansion. And the interval of convergence will be from -1 to 1, and then based on this, we'll either include or exclude the endpoints. That will be given to you. You don't have to memorize that. Okay, -3 choose 0 is always equal to, when you choose 0, it's always equal to 1. So this will be 1. -3 choose 1. Whenever you have p choose 1, you always end up with p. So the first two terms should be pretty automatic. And now we've got some work over here. -3 choose 2. We start with -3. We do repeated subtraction by 1 until we have this number of terms, the k. If it's p, choose k, we do it until we have that number. I might have said terms, like factors. Factors are things that get multiplied together. So 12 divided by 2 is 6. So our next term here is plus 6x squared. And then -3, choose 3. Same idea, start at -3, do repeated subtraction by 1 until we have k factors. The denominator is 3 factorial, so we'll have a 3 that will cancel with that 3. We'll have a 2 that cancels with one of those 2's and the 4. So we'll be left with 2 times 5, which is 10, and it's going to be negative. So this will be our fourth non-zero term. Again, it's a series, so we put plus dot dot dot. And I'm trying to remember, does someone have it close at hand with the interval of convergence? Do we include any of the endpoints when p is negative? I can't remember off the top of my head. The pressure is on. So it's -1 to 1. Someone have it there?
Are you gonna give us that?
I will give it to you, yes, yes. That's always going to be given to you. I know where to go find it, but I can't remember off the top of my head. So while somebody looks that up, then the second part of the problem is going to be something like this.
Neither are included.
Neither are included. Okay. All right, so there is our expansion. There's our interval of convergence. And then what normally we will do is say, okay, now that you've got your generic binomial expansion for a -3 power, now let's modify it with substitution. So our modification with substitution is going to be take all the x's in your expansion and replace them with -x squared. So we're going to come through and do this kind of thing. And often with the binomial one, plus dot dot dot, it's a series. You do, this is one time where we do simplify these coefficients if it asks you to. If it says don't bother, then don't, but
Why did we do this whole -x squared thing? Where'd the 1 minus x squared come from?
so this is a second part of the problem.
Oh, okay.
So the second part of the problem is going to say, now that you have your generic binomial expansion for a -3 power, now if we
Oh, you
modify
use it to
the
find
x,
Okay.
so we're going to replace the x with x cubed, then we're going to have a modified thing here. Let's see. That is going to be positive 10x to the 6 plus etc. So there's our binomial expansion for this modification. Then we also have to modify for the interval of convergence. So we replace the x with the interval of convergence with the same replacement. Turn it into a -x squared. Multiply by -1 is just going to move these inequality symbols the other direction. And that's kind of ugly, so we're going to put it in the more traditional form. This side is always true. That is always true. So it really suffices to come down to that. And then you can take the square root. Both sides are non-negative, so you can take the square root. The square root of x squared is absolute x. And lo and behold, we actually end up with the exact same interval of convergence. So we didn't gain any convergence at endpoints like sometimes happens. So we end up with the exact same interval of convergence. All right, let's stop there. And then the last 4 questions are the ones that we sort of talked about earlier in the class and on Thursday. I'll check email regularly between now and Thursday. You can bring a note card, both sides of a note card, draw some nice pretty pictures, or be super analytical and just write 500 formulas down, whatever your choice is. And I will see you Thursday, unless you want to stay and do more math. Errol, question? Can be what? Yeah, you can print them. I'm fine with that. Yeah, if you want to type them and print them, yeah. Totally fine with that.
Should we have those series memorized that we memorized for the last thing, the E to the X?
So the ones that are going to show up on the test will be those same ones if they're going to show up randomly. I mean, that wasn't listed as one of the questions. So,
90%.
yeah. I mean, writing down a few of those series is probably a good idea, but that specific question where we used it for the limits is not going to show up.
Man, do we remember an
Is it
awful hard
gonna be just based off of
I did, yeah.
like
He
the
was
past
like, yeah, you don't
exams,
need
so
that.
it's gonna be questions for your past exams, or is it just final?
So when we look at it, we should get some